All right, let's just jump right into this explainer and demystify the microscopic culprits behind some of our favorite everyday mysteries. Have you ever wondered why an overfilled cup of water bulges way up at the top without actually spilling over? Or why your salad dressing oil outright refuses to mix with the vinegar, no matter how hard you shake it? Well, the answers all come down to tiny, entirely invisible forces.
Here is our roadmap for today to uncover these superpowers hiding in plain sight. We'll hit 1. The invisible molecular handshakes. 2. Meet the intermolecular forces. 3. Real-world molecular superpowers. 4. The rules of mixing. And wrap up with 5. Measuring solutions and gases. We're starting right at the atomic level and building our way all the way up to complex math and real-world stuff. Let's go!
Section 1. The invisible molecular handshakes. To get this, you really just need to picture molecules as a bustling society of people interacting. Think of a crowded high school hallway between classes.
So the absolutely crucial thing to grasp here is the difference between these two types of forces. Intramolecular forces, think of those as strict family ties. These are the super strong covalent or ionic bonds that physically hold a single molecule together, kind of like family members living under one roof. But intermolecular forces? Those are the handshakes, the high fives, or even just the awkward nods between completely separate molecules as they bump into each other in that crowded hallway. They are the forces acting between molecules, not within them.
Moving right along to Section 2, meet the intermolecular forces. Let's see what these specific molecular handshakes actually look like when things collide.
Just like different greetings in our hallway, these forces come in varying strengths. First up, we've got London dispersion forces. These are the weakest interactions. Honestly, just a passing glance, but they are found in literally all molecules. Period. Then we step up to dipole-dipole interactions. These happen between polar molecules, like acetone. Because one end is slightly positive and the other is slightly negative, opposites attract, right? They feel a genuine magnetic pull. And finally, the heavyweight champion of them all, hydrogen bonding.
Listen, hydrogen bonding is the absolute VIP handshake of the molecular world. It's this supercharged type of dipole-dipole interaction that only happens when a hydrogen atom is directly attached to a highly electronegative atom. Specifically, we're talking nitrogen, oxygen, or fluorine. This exclusive VIP handshake creates incredibly powerful bonds between separate water molecules, which literally gives water the unique, life-sustaining properties we rely on.
And you can totally see how these forces dictate physical properties, like boiling points. Check out ethanol versus dimethyl ether. Ethanol has those VIP hydrogen bonds, meaning its molecules grip each other super tightly. It takes a massive amount of heat energy, up to 78 degrees Celsius, to break those handshakes and boil it into a gas. Dimethyl ether, it only has weaker dipole-dipole forces, so boils off at a freezing negative 23 degrees Celsius. And look at pentane versus neopentane down there. Even with the exact same chemical formula, straight-chain pentane has way more surface area to make contact and form dispersion forces compared to a clumped-up, branched molecule. More surface area literally means more handshakes, which means a higher boiling point.
On to Section 3, real-world molecular superpowers. How do these invisible microscopic interactions actually translate to the visible world we interact with every single day?
Okay, you've probably noticed these little everyday miracles. I mean, a solid metal paperclip is way denser than water, so it should sink like a stone immediately, right? The reason it doesn't is entirely driven by those invisible forces we just talked about.
It's all about surface tension. Deep inside a glass of water, a molecule is happily pulled in every single direction by its neighbors. But at the surface, it's a different story. Because the molecules at the very top aren't being pulled from above by the empty air, they panic a little and grip their side-by-side and downward neighbors extra tightly. They form this invisible, highly cohesive, resilient skin. That's what floats the paperclip, supports water-walking bugs, and makes an overfilled cup bulge at the rim.
Actually, to put that into perspective, get a load of this number, 43. Thanks to the massive cohesion provided by those VIP hydrogen bonds, you can pile a mind-blowing 43 individual drops of water onto the surface of a single penny before gravity finally wins and it spills over. No way, right? Try it sometime.
Now, these forces don't just mess around in liquids, they act as the ultimate architects in solids too. When materials freeze, atoms pack together into rigid little structures called crystal unit cells, and they do it with crazy varying efficiency. A simple cubic structure only manages to fill 52% of the available space. Body-centered cubic bumps that up to 68%. And the face-centered cubic? That's the masterclass.
It packs atoms together tightly to fill an incredible 74% of the space, leaving almost no empty volume behind.
Section 4. The rules of mixing. So what actually happens when we force different molecular societies to mingle together?
Well, the golden rule of solubility is pure high school clique drama. Like dissolves like. Highly polar molecules only want to hang out with other polar molecules. Nonpolar molecules stick strictly to other nonpolar ones. They absolutely do not mix across clique lines. Because water is so polar, it easily mixes, or if we want to sound fancy, it's miscible, with polar substances like ethanol or hydrochloric acid. Water will literally tear apart the super strong ionic bonds of table salt because its polar charges surround and carry the salt ions away. But try mixing water with nonpolar hexane or oil, total rejection. They are immiscible, stubbornly separating out into completely distinct layers.
But here is where it gets interesting. What if a molecule has a bit of both personalities? Well, small alcohols like methanol are highly soluble in water because their polar half dominates the relationship. But if that alcohol grows a long, bulky, nonpolar carbon tail, like you see in 1-butanol or 1-octanol, that big nonpolar tail acts like a massive barrier. It literally bullies and overpowers the polar part, stopping the molecule from mixing with water entirely.
And that brings us to our final stop, Section 5, Measuring Solutions and Gases. Let's do a little math to calculate the strength of solutions and then see what happens when gases decide to break all the rules. Say you're tackling some intensely dirty laundry and you need to use a polar molecule like hydrogen peroxide to blast those stains. You need to know its strength, right? Enter molarity. It's just the moles of solute divided by the liters of solution. So if you need to dilute a super strong 0.88 molar stock solution of peroxide down to a gentle 0.1 molar solution for a big 38-liter laundry tub, you just use this neat little life hack. M1V1 equals M2V2. This quick mathematical progression tells you exactly what you need. Just add 250 milliliters of your strong peroxide to the tub, and you're good to go.
Okay, we've talked liquids and solids, but what about gases? The ideal gas law assumes gas molecules are just these tiny, insanely fast-moving, dimensionless points that literally never interact or feel any handshakes. But, come on, that's just an imaginary model. In the real world, if you put a gas under heavy pressure or cool it way down, the molecules get sluggish. They slow down enough that they finally get close to each other, and bam! They suddenly feel those dipolar dispersion attractions.
Because those real-world attractions pull gases off that perfect ideal model, chemists actually have to correct the math. To do that, they use the van der Waals equation. This brilliant formula literally patches the ideal gas law using two specific constants. Constant A accounts for the specific intramolecular pulling strength of the gas, and constant B corrects for the physical bulk or size of the gas particles. It's basically a reality check for gas math.
So, as we wrap up this explainer, I really want you to take a second and look at the world around you. From the DNA and proteins in your own body acting like perfectly fitted molecular locks and keys, to the water brewing in your morning tea, these invisible molecular handshakes hold our entire macro world together. It's like a giant puzzle happening right under our noses. So what does this all mean? It means you should keep questioning, keep observing, and absolutely keep exploring.